welcome to the notes for solubility equilibrium. We're going to be talking about calculating KSP. Now KSP is going to be involved with or have something to do with all of these things I've got listed here. Tooth enamel, flavoring of foods, formation of stalactites and stalagmites. If you can tell me which one is which, maybe we could work out a deal for a extra credit point or something, without looking it up, of course. KSP is also involved in GI testing and many other things. Now, right now, what I'm going to do is kind of switch gears. I'm going to pause this video and switch over to a little video animation that I have of a salt shaker in water.
Alright, so we've got this salt shaker, and what is in it is sodium chloride. So what happens if we put a little salt into the water? It's going to go ahead and dissolve right away, right? And what happens then to the salt crystals is that they are separating into ions, the separate ions, and you'll hear that word a lot in the this upcoming video. But what happens here then if I add a whole bunch? Just like when I showed you that video, we've got the salt crystals. It's a supersaturated solution, but you can see that there are still the ions of sodium and the ions of chloride dissolving off and some reattaching or recrystallizing to this solution. And we've added too much salt that not all of it is going to dissolve anymore. But there still is an exchange of ions going on here. And this water only has a certain solubility, which is a certain amount of salt that can dissolve at a certain temperature for the water.
So when we have, from that video, to write out the equation for it, we've got sodium chloride, which is a solid, dissolving or breaking up into positive sodium ion and a negative chloride ion. Okay? That word ion is going to be important to remember there. Okay? Let's take a look at this dissolving equation as well. We've got calcium fluoride, which is, again, a solid, dissolving into a +2 calcium ion and a -1 fluorine ion. You're probably looking at that going, now, wait, Miss Hummelgard. That is something I actually remember, that fluorine should be a diatomic. So why aren't we writing it as F2 instead of 2F? Well, we are not going to show it as diatomic because when we start over here, we have 3 components. We've got a calcium with 2 fluorines bonded, one on either side. And so then when this breaks apart, we take and break our bonds. We're left with 1 calcium and 2 fluorines. Okay? 1 calcium ion, 2 fluorine ions, with a -1 charge. Alright? So hopefully that makes a little bit more sense for you. And let's go ahead and try these on your own. We want to dissolve them . So we're going to take these solids and break them apart. Go ahead and pause the video and try this on your own. And since I'm still here, I'm going to go ahead and try these out. Alright, so I've got barium sulfate solid, and I want to break that apart. So I've got barium, and let's see here. There's no subscripts on these on the outside of this. Sulfate has to stay together. It's going to be SO4 always. But there's nothing outside of the parentheses, so I know that these should be reduced then. So our barium should have a +2 charge, and it is now aqueous. When we're doing these, we do always need to write out the states of matter. And then our sulfate, our SO4, is a -2 charge, and it also is aqueous. Okay, and the reason that I knew that it was reduced is because my trusty polyatomic chart has sulfate right on it, and it tells me its charge should be -2, but when there's no 2 by the barium, I know that it's been reduced. So looking at this next one, we're going to dissolve or break apart this solid compound into sodium, which is a +1 ion, so aqueous, and then sulfate. Remember, if we uncross the charges, after this one's in the parentheses, if we uncross the charges, that's going to easily tell us sulfate is a -2 charge. And we do need to balance this, so it should be 2 sodium ions and 1 sulfate ion. For this last one here, get rid of this so we can still see it. We should have a calcium. Let's see here, we need 3 calcium plus 2 ions, which are aqueous, and 2 phosphate ions, which are a -3 charge. Again, if you're kind of confused or wondering where I'm getting these numbers at, I'll show you here. This next one, or this last one here, we've got to take these numbers here and uncross them up to the top, and that is how we find our charges. So why is solubility discussed with equilibrium? If you think back to the one video that I showed you of the solution that was saturated, or supersaturated actually, it actually had components dissolving and recrystallizing through the solution there. So I'm going to write something down here. When you're saturated, you're going to be in an equilibrium of dissolving and not dissolving. So you're going to go back and forth from dissolving to recrystallizing or not dissolving, like I wrote down there. So let's try this. Write down the equation for the dissolving of mercury 2 bromide and include the states of matter. So I've got mercury 2 bromide. That's going to be a solid. And, sorry, this is going to be in equilibrium because it's going to be dissolving, not dissolving. Mercury is going to be a +2, and it's now aqueous, plus 2 bromide, -1, also aqueous. Okay. Now, moving on to our KSP. Our KSP is going to be our solubility product constant. And again, we're got our misspelled K there. So KSP, the SP stands for solubility product, and then the K is constant. I'm going to go back to the video now, and also going to show you our solubility chart. With the solubility on this video that I'm showing you, all salts, remember, all chlorides, are soluble except those of silver, mercury, and lead.
Alright, so now we're going to the slightly soluble salts, and the one that I've got here is mercury 2 bromide. If you look off over to the right hand side of the screen here, we've got mercury 2 bromide, and now I'm going to try and shake in as much of that as I did of the sodium chloride so that we can see kind of what's going on here. Alright, so you'll notice that I shook in probably even less than what I did with the sodium chloride, and right away we've got a giant clump of the mercury 2 bromide in the water. So even though I'm putting in the same amount, not as much of it dissolves as with the sodium chloride. There still are particles dissolving off and recrystallizing from both the mercury 2 and the bromide, but it doesn't happen quite as quickly as with the sodium chloride. The mercury 2 bromide is not as soluble. It's only slightly soluble.
Our KSP is going to be a ratio between how much dissolves and how much doesn't dissolve. And, lucky you, we are going to have the same rules as equilibrium expressions, meaning solids, pure liquids are not going to be included
In our expressions.
Alright, so writing KSP expressions. We have copper 1 bromide. Let's write the expression for that. So now KSP, and I'm just going to go ahead and cross out my reactants there because it's a solid. And what this means, since it is in equilibrium, it means it's slightly soluble. I'll write that in red. Alright. So, to do our KSP then, we've got copper 1, times our bromide ion, which is a -1 charge. Okay, so this is a KSP expression. Why don't you try this one on your own? Pause the video and see how we do. Okay, take note. I forgot to say that this is a solid, but of course, when we're dissolving and dealing with KSPs and solubility, we're always going to start with a solid there.
Alright, so when we're talking about these relative solubilities, we're not going to calculate the KSP, but we will look at and interpret the relative solubilities of these three substances. They aren't very soluble, as you can see from the exponents, but we can still put them in order from most soluble to least soluble, or least soluble to most soluble, by looking at that exponent and saying which number has the smallest KSP. So what this means is actually that there are this is our number for this KSP. For 5 times 10 to the negative 12th, we have that as our number. So you can see this is a much smaller number. There's a lot more decimal places. So this one here is going to be least soluble. This would be our second least, and this would be our most soluble. And you can see that because of our -5 exponent is going to make this a larger number than both of these two numbers. So these solubility, when we're talking about which one is the most soluble, which one is the least soluble, you're not going to have to memorize these numbers here. You will always be given them, and not in any particular order, but I will usually ask you which one's least soluble, or put them in order from least soluble to... Alright, so please do those, or that last problem for homework, if you will. If you're in class and you have it done, turn it in, great. If not, turn it in tomorrow, Thursday. That is your assignment, is to finish up that last problem, least to most soluble. And also, if you're having issues with anything else, make sure you come in and get some help.